What do equations sound like when you play them on the piano? They might sound like that. This is the K-12 Engineering Education Podcast. I'm your host, Pios Wong. Today, let's learn about how to listen to two-dimensional mathematical equations on the piano. Part 1. Coordinates. Let's talk about coordinates and the coordinate plane. You might know the coordinate plane in math. Close your eyes and picture it, or just draw it out, or Google it if you can. It's that flat system or grid with a bold horizontal x-axis and a bold vertical y-axis, and these two axes cross. You can graph points and curves in this plane. In algebra, science, business, and so many other fields, we spend a lot of time graphing important stuff in there because it helps us visualize data and two-dimensional relationships. It makes those math equations with x's and y's in them a little more real and a little less abstract. Okay, so if you can see data and equations in the coordinate plane, can you hear them too? Yeah. For example, let's hear the point 0, 0, which says when the first number x is 0, the second number y is 0. It's so special that we give 0, 0 a name. It's called the origin. It's right smack at the intersection of the x and y axes on the coordinate plane when we look at it. Here's what it might sound like when we listen to it. How did we translate that point on a graph into a note on the piano? First, the x value used to say where you are on the graph, left and right. Now, x is time. It tells us how much time passes before we play a piano key. And the y value used to say where you are on the graph, up and down. Now, y is pitch, or basically how far you are up and down the piano keys. So let's say for now, when x equals 0, we are 0 seconds from the start, with no delay. Don't wait to play something. And when y equals 0, we're going to play this key. That's what musicians call middle C. It's got a pitch name of C, and it's sort of in the middle of your piano, give or take. Just like in a visual graph, you can change where your 0 is, but let's leave y equals 0 at middle C for now. Okay, so let's talk maximum and minimum values now. What are they? On a visual graph, that's like the edges of your paper, or the edges of your graph, beyond which we can't draw nor see. They're the least and greatest values that your graph can display. In our audible graph, let's define the maximum and minimum values we can present on the piano, at least for the next examples. Let's say, for the x values, we'll go from 0 to 10, where every unit is 1 second. And for the y values, we'll go from negative 23 to positive 28. Negative 23 to positive 28 matches up with all 52 white keys on a grand piano, with middle C as 0. We just defined our audible coordinate system. Let's hear what it sounds like. First, let's remind ourselves that the coordinate 0, 0 sounds like this. 0, 28 sounds like this. There's that highest note played 0 seconds after the start. And 0, negative 23 sounds like this, at the lowest part of our y values. Let's try something a little different. Let's hear what the coordinate 3, 5 sounds like, starting now. Hear that delay? We hit that piano key only at 3 seconds, and we played the 5th key above middle C. That's 3, 5. It might be easier to hear the timing if we had some audio markers for every unit of time, kind of like the tick marks on an axis in a visual graph. So we could use a snare drum to keep count while playing 3, 5 if we wanted to, like this. Is that easier to hear, 3, 5? Or just more complicated? It's kind of a personal choice. But for now, let's go back to listening without those audio tick marks. What do you think the coordinate 2, -7 will sound like? Take a moment and try to hear it in your head. Here's 2, -7. Okay, good job. What about a sequence of coordinates? What will these 3 coordinate pairs sound like? 0, 0, 1, 2, and 2, 4. Again, that's 0, 0, 1, 2, and 2, 4. Let's listen. And go. One more mini challenge. What will these next 3 coordinates sound like? 1, 3, 1, 5, and 1, 9. 1, 3, 1, 5, and 1, 9. Let's listen. And go. You just heard a chord, which in music is when you play multiple notes all at the same time, superimposed. Mathematically speaking, chords happen when all our time coordinates are the same, or all our x values are the same, in this case at x equals 1. Graphically, if you picture this, that's 3 points vertically lined up above each other, kind of like the notes on a music staff. All right, we talked about playing individual coordinates. Let's do a whole bunch of coordinates now, in sequence. We're ready to move on to equations. Part 2. Linear equations. What is an equation? It's a relationship. It says when x equals something, then y is going to equal something else, for example. Using equations, we can even link x and y together predictably, where if we know what x is, then we can do some math on that x and figure out y. Take the basic intro to algebra equation, y equals x. It says that our y value is exactly equal to the x value. So if x equals 1, then y equals 1. If x equals 2, then y equals 2. If x equals 3, then y equals 3, and so on. You have a whole bunch of coordinates you could plot from this. 1, 1, 2, 2, 3, 3, and so on. When you graph all these coordinates and look at it, it makes a line. It's what we call linear in math. But let's hear this graph on the piano. How come this equation, y equals x, sounds like that? Well, when x equals 1 second, y equals 1 on the piano. When x equals 2 seconds, y equals 2 on the piano, and so on. But you know, this is too slow. We're going to speed things up by modifying our x scale. Instead of our x values being in whole seconds, let's just make them quick beats. And 1 beat is always at a steady, even fraction of a second. So now, let's listen to y equals x again on the piano, where the x values just represent 1 short beat. It's a little easier to hear, right? And can you hear the pace at which the pitch is moving? We're traveling up the piano keys steadily at 1 key per beat. That's what we call slope in math. Slope is a steady change in y for every unit of change in x. You might have heard that before. So let's listen to another linear equation, y equals 2x. What will that sound like? And go. Do you hear the pace of increase in pitch this time? It's faster. It's still steady, but it's actually moving 2 keys per beat this time. The slope is bigger. And so what would another linear equation sound like? Let's try y equals 5x. And go. Was it what you expected? How did that slope change? Let's modify our equation a little more. What if we throw in a negative number multiplied by x? Let's listen to y equals negative 2x. So the y values are always going to equal negative 2 times the x value. So if x equaled positive 5, for example, y would equal negative 2 times 5, which is negative 10. Again, what will the equation y equals negative 2x sound like? Y equals negative 2x, playing now. You heard that, right? What's different there? In math, we say this linear equation has a negative slope, still steady change, but we're moving down the piano this time. I think you get the basic idea about what linear equations sound like. We could still talk more about lots of other math concepts here, like y-intercepts and discrete versus continuous functions and whatnot, but let's just take a pause on the math briefly to talk a little bit about English, and then music. Then we'll get back to the math. Part 3. Let's streamline our vocabulary. What's the word that means to make visual? It's visualize. For example, we said earlier that when we want to make data and equations more visual, we visualize them on a graph in the coordinate plane with lines, points, and maybe colors and labels, and all that stuff that becomes a visualization, a feast for our eyes as much as for our brains. So then, here's the important question coming now. Since we're doing it in this podcast, what's the word that means to make audible? To make something audible. Audible-lize? I don't know about you, but my vocabulary eludes me here. Where is the English verb or action word that means to make audible, or to make hearable, or to make something richly perceptible through your ears? If we can visualize an equation on a graph, we should be able to an equation on a piano. What word fills in that blank? Is there no word for this in our vision-centric English language? Many people have asked this question before. And if you search on the internet, one suggested word to use is amplify. But is that quite right? To amplify something is to make something that is already slightly audible even louder or more audible. Try as I might, I can put a microphone up to my linear equation that I've written, and I still can't hear it. Is this thing on? Do some more searching in scholarly research articles about technology, and you might find another word that just might work. Sonify. Let's get some context. Professor Philip Cordham is in the psychology department of Rice University, and in 2008, he wrote a book on non-graphical user interfaces in technology. And in it, Professor Cordham said, recently, auditory interfaces have been employed as a substitute for more complex visual interfaces, and the term sonification has been coined to describe these kinds of auditory interfaces. In a sonified interface, representations that are typically visual, such as graphs and icons, are turned into sound, that is, sonified. I like how Dr. Cordum uses passive voice there, saying the word sonify was coined. Not like I coined it or he coined it or something, because who really knows who first used the word sonify in this way? If you search in Google's Ngram viewer or Google's database of word usage in published books, the words sonify and sonification enjoyed a popularity increase starting around the 1960s or so. Maybe a bunch of technologists started using it then. Regardless of the etymology, I really like this word sonify that Professor Cordum is referring to. It says succinctly what we're doing when we try to represent mathematical relationships as melody. So I'm going to use it. Today, we are sonifying equations. Part 4. Musical Scales. Remember what our linear equations sounded like? That's y equals x again. Did you notice how those tones felt emotionally? Always kind of like, la la la, I'm fine and dandy. Well, that's what we call a major scale that you're hearing as y increases along with x. Specifically, it's the C major scale, all the white keys on the piano. But there's no reason why we have to sonify our y values into a major scale. We could sonify it into a C minor scale, for example. Y is still increasing along with x. It's still the equation y equals x, but we made an arbitrarily different musical choice for how to represent possible y values. In this case, we translated our y values into the sadder or spookier scale of Western music. We can also try to use all 88 keys in our grand piano for our linear equation. That's all the black and white piano keys. We call that the chromatic scale. With 88 keys at our disposal, we could make the range of y values go from -39 all the way up to +48. I'm speeding up the beat here because 88 keys could take a while to play if we're too slow. How does the chromatic scale feel to you? So far, we've heard the major, minor, and chromatic musical scales for our y values in our linear equations. And we actually have so many more choices of musical scales: pentatonic, mixolydian, quarter-tone. Each one with its own cultural history and subjective emotional feeling. And we didn't even get into changing the timbre or voice of our notes. That's a slow, old, creaky piano with a sustain pedal held down. These musical choices in sonifying our equations are pretty special and unique, because visual graphs might not tickle our brains in the same way, even when using different colors and paintbrushes. All these choices aside, if we're going to sonify and compare a bunch of different math equations on the piano, we have to be consistent. So let's make firm choices as we go back to the math. Let's keep it simpler for now. We'll stay with that C major scale on our standard piano. But feel free to imagine or play along with those other musical scales and choices on your own when you get a chance. Part 5. Polynomial equations. Let's analyze the sonifications of equations that mathematicians call polynomials, starting with one of the most basic ones, the quadratic equation y equals x squared. So when x equals 1, y equals 1 squared, or 1. When x equals 2, y equals 2 squared, or 4. When x equals 3, y equals 3 squared, or 9, and so on. So here's y equals x squared sonified. That was quick. Did you catch that? Let's play it again. What did you hear? Yeah, the pitch y is increasing faster than the beat x. It's like we're accelerating up the piano keys, not steadily moving like in those linear equations. Let's slow this equation down a bit and multiply it by a fraction. Let's sonify the equation y equals 1/10 of x squared. Okay, that slowed it down, but we can hear it's still accelerating. Let's point out something here. Right now, we are actually forcing our piano to play a piano key at exactly each beat in time. That means we have to round our y values so that we go to the closest piano key at any point in time. This sonification is really an estimate to keep a steady rhythm. To be more exact, we could just play the piano notes right when they're needed. We don't have to just play on the beat. We might not get a steady rhythm, but we do get the exact piano notes. So let's try listening to our quadratic equation again with a free rhythm. Here's y equals 1/10 x squared. That's easier to hear the acceleration. It was slow in the beginning, but picked up speed as we went along in time. A key feature of quadratic equations with an x squared in them. And let's listen to another feature of quadratic equations. To do this, we have to change our x scale or our time scale to include negative numbers. From now on, we're going to start our x values at a negative number. X is going to go from negative 16 as our minimum value up to positive 16. So for example, when x is negative 16 at the start of our sonification, y equals 1/10 of the square of negative 16, or about positive 26. Here's that sonification. That was y equals 1/10 x squared. What did you hear that was special? The pitch decreased quickly in the beginning, then decelerated, then hung out a bit around middle C, started increasing, and then continued accelerating back up out of range of the piano. That's the sound of what mathematicians call a parabola, where you change directions like that. And that point down at the bottom, where y was changing directions, that's the vertex of this equation. So in this particular case, the vertex was at the time x equals 0 and when y was 0. You can hear other types of quadratic equations too. Here's y equals negative 1/4 x squared plus 20. Did you notice how the negative 1/4 in this equation changed things? The y values, or pitch, started out really low this time. Then they went up and back down again. Did you hear the vertex there? And so the key parts of polynomial equations like these are that the y values might change direction partway through before finally flying off quickly into one direction or the other toward the edge of the piano. Now, let's listen to a cubic polynomial, or a polynomial with an exponent of 3 on the x. And let's use the same numeric scales approximately for x and y that we've been using. Let's sonify the equation y equals negative 1/100th x to the third power minus 1/5 x squared plus 3x plus 3. How many times did that melody change direction? Twice. The pitch changed directions twice. And if we sonify polynomials that have an exponent of 4 on the x variable, we might hear 3 changes in direction. Can you summarize the pattern for what we would hear when we listen to different polynomials with bigger exponents in them? That's for you to think about. Part 6. Repeating patterns and musicality. Do you remember that iconic Chili's commercial with the baby back rib song?
I want my baby back chili.
It was part of many a 90s American childhood and was spoofed a lot afterward, like in the TV show The Office, when Steve Carell and Tim Meadows started singing it.
I don't think Christian has time for that.
I have
Don't
time.
let me
I want my baby back, baby back, baby back. I want my baby back, baby back, baby back. I want my baby back, baby back, baby back. I want my baby back.
It's as if just repeating something over and over can kind of make it music. So, musically speaking, it's really interesting to analyze how you can make repeated melodies using a mathematical equation. What equations do you know that have a repeating pattern? Did you think of some? Let's sonify them, find patterns, and attempt to make music. All right, we're going to advance our math level and analyze y equals sine of x. Sine, S-I-N-E, is a trigonometric function related to the ratios of the sides in a right triangle, and we're going to sonify y equals sine x by using an x scale of -23 to +28. To sort of match up with our y scale of -23 to +28. And we'll also keep that free rhythm, playing exact piano notes as soon as they come up. Let's listen to y equals sine x. What's unique about this sonification? It certainly repeats. The value of y also only goes from -1 to +1 the whole time, naturally because the sine ratio can only go between those values. If our goal is to find some music in math, this isn't going to cut it. How about increasing the amplitude? Let's try y equals 16 sine x. What do you hear now? That's an increase in amplitude, all right. Let's take this and add a positive offset of 12. What do you think this next equation will sound like? Y equals 16 sine x plus 12. Let's hear it. You can hear how mathematical amplitude and offset affect our cyclic sine waves. Musically, is there anything interesting there for you? Now that we've heard how repetition might help make music, let's think about another rhythm again, and intentional silence. So far we've heard sine waves where we played basically all the piano notes as soon as we could. But let's hear that last sine wave function again, but with a steady rhythm, playing one piano note for every beat. Let's listen. Musically, is there anything interesting there for you? It was basically the same function, but we weren't playing as many y values. In science and math terms, you could say we were sampling the function at a steady sampling rate. It just goes to show that making use of silence and rhythm also helps make music. Let's hear another example to analyze the effect of sampling, silences, and rhythm on our sonifications. We're going to listen to the tangent function next, and you trigonometry experts will know what that is again. Here's the equation y equals 5 tan of 1/2 x. with a free rhythm first, playing every piano note. Those flourishes up the piano keys, those are close to what musicians call glissandos, although these have an irregular rhythm. And when you hear the Y values going really high toward positive infinity, then jump back to the bottom from negative infinity to rise again, we are hearing what mathematicians call an asymptote. Now listen to the same tangent equation again. Y equals 5 tan 1/2 x. But with a steady rhythm instead, forcing it to play a note for every beat, but not between beats. What do you notice in there? What's different in how that hits you when you don't hit every Y value? Do the silences between the Y values change things? Is there anything musical to you in there? Is this nascent music? So far, our math equations have demonstrated repetition and rhythm as contributors to music. Let's talk about harmony next, or when you play two melodies on top of each other offset a bit. First, let's play the melody from a sonified square wave. As the electrical engineers know, a square wave is based off a sine or cosine wave, but basically rounding the Y values up or down. Here's a sonified square wave with an amplitude of 2 and offset of 2 in a steady rhythm. It's pretty simple, right? The same two Y values or pitches played on repeat. Now let's hear a second melody from a sonified square wave with an amplitude of 2 again, but with an offset of 4. It's a little higher pitched because of that bigger offset. Now let's superimpose these two square waves on top of each other and listen to them together. That's harmony. We're hearing what musicians call a major third interval played during each note. And this has its own color and feeling, compared to, say, a minor third interval harmony, heard here. In a minor third interval, the offset of that second function is just a little smaller. Bigger and smaller intervals of musical harmony give different colors to the sound. Mathematically, if I gave you an XY equation, could you give me another equation that harmonizes with it? How? That's right, you could add or subtract an offset to my equation and play both equations at the same time. That's a straightforward way to do it. Let's stop there with the repetition, rhythm and silence, and harmony. I'll leave it to you to explore how to represent more features of music in our mathematical equations. Part 7. Statistical functions. Out of the many types of equations we could sonify on the piano and analyze, let's get out of the realm of algebraic functions and trigonometry. Let's end with a few statistical functions. We've been using the word function without really explaining it, but now's a good time to remind you or introduce you to the idea that a function in math has only one y value for every x value. No chords in a sonified function. And so I can make a function that says y equals any random number at any x value or at any point in time. Let's hear what this function sounds like on the piano if y equals any random number between negative 23 and positive 28. Here it is. What do we hear in there? To be more specific, we heard a uniform distribution of y values, meaning the notes played at any point in time are randomly between the lowest key on the piano and the highest key on the piano, and any white key has equal chance of being chosen. This is one of those cases where a computer can play this statistically random melody more easily than the average human pianist. We can narrow the window of the uniform distribution too. Let's listen to a uniform distribution of y values, but restricted to -10 to +10. What do you hear now? Yes, still a random pattern, but within a very clear-cut, predictable window of piano keys. And any one of those keys in the window have an equal chance of being pressed. There are other types of randomness, though. What if the piano keys don't have an equal chance of being pressed? What if just the keys around middle C have the highest chance of being pressed, closer to how a human might play a random melody when you're sitting right in front of the center of the piano? Let's listen to this type of random function. What do you hear? Is it different from the uniform distribution? This function that we just heard has a random distribution of y values, but it's what mathematicians call a normal distribution, or Gaussian distribution. It means that most of the y values are hanging around a central value, in this case 0, or middle C. It's a little more difficult to notice, but the notes in the middle of the piano were being played most often. But occasionally a note farther away could play too, just not as much. Statistically, this was a random normal distribution of y values with a mean of 0 and a standard deviation of 5. We say that normal distributions are centered around the mean. So what do you think it would sound like if we sonified a random normal distribution with a mean of -8 and a standard deviation of 5, same as before? Here it is. The y values are clustering around the -8 note. And what if we keep the mean at -8, but now shrink the standard deviation to 2 instead of 5? What would that sound like? It's still centered on the mean y value of -8, but we've tightened up where the notes play. There's not as much variability in how far out from the mean we play. Now that we've analyzed how different aspects of randomness sound on the piano, how much randomness exists in music? What other aspects of randomness in music would you want to analyze mathematically next? Part 8. Review Quiz. In this overview, we've thought a lot about basic concepts in music and math. Let's quiz ourselves on what we know. First, I'm going to play some equations with possible x values going from -23 to +28, with every beat spaced out exactly 1 unit apart, and possible y values going from -23 to +28 across all the white keys of the piano in a steady rhythm. You have to figure out what these equations are as best you can. Number 1. What equation do you hear in this next sonification? If you said it was a sine or cosine wave, good job. Those trigonometric functions could both sound like that. It also has a negative offset. Specifically, it was y equals 5 sine, open parentheses, 1/2, open parentheses, x minus 4, closed parentheses, minus 5. Number 2. What equation is this? If you said linear equation with a negative slope, good job. Specifically, that was y equals negative 2x minus 20. Number 3. What equation is this? If you said linear equation with a negative slope again, that's right. The slope is shallower though, at just negative 1. This equation was just y equals negative x. Number 4. What equation is this? If you said quadratic equation or a polynomial with the highest exponent of 2 on the x, that's correct. It also has a negative coefficient on the x squared, which you can hear as the pitch goes up, then back down. This equation specifically was y equals negative 0.08 times the quantities x minus 8 and x plus 16. Number 5. What equation is this? If you said that's a square wave, that's correct. And it's got a coefficient of 6 in the front, increasing the amplitude or difference between the y values. It also has an offset of negative 5, which you can hear since this square wave is lower pitched and centered around the negative 5 note. Number 6. And this one will be slightly different. Maybe easier if you have more experience with graphing. I'm going to ask you to imagine what a circle sounds like sonified. To clarify, a circle is not a function since there can be 2 y values for every x value, but you can still play it on the piano. Take a moment and think about it. Ready to listen to it? Here's the equation of a circle, sonified with a steady rhythm on the C major scale. Did you imagine that? 2 notes at one time, except at the very beginning and the very end. It's like there's a left and right hand playing mirror image melodies, like the top half and the bottom half of a circle. For the math people keeping track, the equation was for a circle of radius 16 and centered on the origin, or x squared plus y squared equals 16 squared. Maybe you imagined the sonification of a circle in a free rhythm. Let's hear that version too, just to check if it matches with what you were thinking. So, similar concept. 2 melodies on top of each other, diverging, slowing down, and then converging, meeting back at the y value from which it started, middle C. Okay, just a couple more questions left in this quiz now. This one is related to music. Number 7. I'm going to play a cubic polynomial. Tell me what kind of musical scale you hear in this sonification. That's a chromatic scale. That's when we use all the keys on the piano, including all the black and white keys, and we hear smaller intervals in our pitches. For a bonus question, how do you think this equation would sound on the C major scale? You can check that out yourself. Okay, number 8, and it's getting hardcore now. Are there any real songs or song melodies that you know that you think you could model with an equation? Are there any songs that sound like a math equation? What song is it? And what equation would you use to model it? This is a question that you should do for homework. It's like a project. Listen to music, all sorts of music. See if you can identify pieces of a tangent function somewhere, or a random splash of notes somewhere else, or the rise and fall of a quadratic equation. This could take some time. So bookmark this one and let's go on to the last question for now. Number 9. Are there any equations in math that you can sonify and that inspire you to create music? What equation is it? And what music would you make from it? This is another biggie. You know what to do. Take your time, get creative, hear those sonifications of equations again, and come up with something new musically. Let's see what you can do. In closing, you went through 8 mini lessons in math and music, so congratulations. Hopefully you'll continue the learning on your own. If you want to explore sonifications of 2-dimensional equations on the piano yourself, you can use my tool that I created online. It's free, open to everybody, and available at this website, pioslabs.com/Chordinates. That's pioslabs.com/CHORDINATES. Pios Labs is my independent studio for engineering and education in Austin, Texas, run by yours truly. And Chordinates is spelled like chord, as in musical chords, combined with the math word coordinates. Links to the Chordinates web tool are in the show notes, along with direct links to many of the functions you heard on the piano today, so you can play around with them yourself. This web tool is always evolving, and I plan to add more equations, more musical scales, and instruments, stuff like that, over time if people are into it. I also appreciate your feedback on my Chordinates tool, as I need users to tell me how to make it better, whether you're a teacher showing it in your band class or a student reviewing algebra with your friend. I need the design tips. So thanks for sharing them with me. That's it for this lesson. Thanks once again for listening to the K-12 Engineering Education Podcast. This has been Pius Wong, engineer and educator, hoping that you'll mix it up with more math and music wherever you are. The K-12 Engineering Education Podcast is sponsored by my studio, Pios Labs in Austin, Texas, and also by the Engineer's Guide to Improv and Art Games, available through Amazon and other booksellers. This show is also made possible by very cool people donating to the show on Patreon each month. Help me continue the podcast by becoming a patron at patreon.com/PiosLabs. Visit the podcast website for show notes, links, transcripts, and more. Go to k12engineering.net. That's k12engineering.net.